Hey, howdy everyone, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I record every one of my lectures, the same lectures I teach within the classroom, to support my students, to support working professionals, or anybody who wants to learn more about data analytics, geostatistics, or machine learning. I think it's a great thing to just break down some barriers and just share this knowledge with everyone. Okay, so this is the first lecture in the course Data Analytics and Geostatistics, Spatial Statistics, and we've already talked about fundamental statistical concepts, sampling. Now let's talk about data types that are commonly available to us. You'll notice there is a bias here with regard to the types of data types you would have for subsurface development of resources, oil and gas specifically, but could be used the concepts for many different settings, of course. Okay, let's talk about data dimensionality. Now, this is a challenge. This is part of the big data challenge we have with a variability of our data, different data types that we have to cope with and work with. So, we have a lot of 1D, 2D, and 3D data that we need to work with. And so, for example, one-dimensional data is commonly available to us in the form of well logs along a bored out well within the subsurface or drill hole through the subsurface. So we've cut a hole through and now we're able to sample along that hole. Now, the most commonly available information will be a well log where we've sent a tool down the hole and we pull it back up, and as it comes up, we make some type of indirect measure of the subsurface. Gamma ray can tell us about the amount of shale. Neutron density can be an indicator of the amount of pore space or porosity. And we might even have other information like injection and production information. We might be logging production along a well. One-dimensional data that we work with in space, you can imagine it can be very complicated. A complicated trajectory moving through the subsurface, and we have information just along that. We also often deal with two-dimensional information. It's very much like an image for those of you working with data analytics and machine learning on images. Geologic maps in plan view, looking down at the setting, often it'll be in plan view, a map. Seismic lines will be a cross section. We often in exploration settings still have just some two-dimensional seismic lines that are shot. So we're only seeing a cross section like shown here of what's going on in the subsurface. We could also even have thin sections, which are super, super cool, where we take extracted core and we cut it very thin, and we're able to actually look at it, see the void space, see the pores, see the mineralogy, see the cementation, and so forth. That's really cool. And we often also have three-dimensional data sets. Most commonly would be our three-dimensional seismic volumes. So right in here, we've got a set of seismic. These sections right here, in fact, are from a full three-dimensional seismic survey. And we may also go beyond the one-dimensional data from well logs by doing well-to-well correlations and building out a framework. At that point, we do get to the point where we have a three-dimensional, albeit interpolated and estimated between the data, representation of the subsurface. The reservoir model, or the mineral mining resource model, or the groundwater volume in place and pressure model, all of these would be three-dimensional models too, generally. And so their representation of all the data, the 1D data, the 2D data, the other 3D data, all integrated together to get a three-dimensional full representation of what could be going on the subsurface. We'll probably model with some degree of uncertainty. Maybe we ignore that with estimation. Maybe we account for it with a simulation method. We'll get into that more later. And of course, if you're trying to do some type of transfer function, such as flow analysis or volumetric, we need those full three-dimensional models most of the time. And data variety is a criteria for big data, and we will deal with a lot of different data types. We'll get into it right now. Now, if we try to classify features or variables, we could break them up into some really interesting groups. First of all, categorical and continuous. Now, I like those terms. I find them very useful to me. Categorical would be we could break that up into nominal and ordinal. Now, categorical nominal suggests that we have unique discrete classes or bins, but they have no ordering relationship. Sandstone, limestone, or boundstone, wacky stone, whatever it is, there's not a natural ordering to it. And so they're just groups. They're just different groups. That's categorical nominal. The categorical ordinal would be there's natural ordering. We may bin up geologic time, but there is a order to it. We go from the Paleozoic to the Mesozoic to the Cenozoic. You see that, right? All right, so categorical. Some will call categorical qualitative. You'll see later on I use a different definition, which is commonly used within geostatistical literature. I'm consistent with them. The continuous, we can deal with interval and ratio-based continuous features or variables. Now, in the continuous, to think about continuous, we don't have bins. We have a minimum value, an upper value, and all possible values on the number line can be used, up to some limit on precision, of course. Okay, so that's continuous. Now we have different types of continuous features. The interval-based approach, there's a consistency. If I go from 0 to 10 and 10 to 20 and 20 to 30, there's the same amount of change. It's consistent, but there's no physical meaning to the numbers. We've picked an origin, we've picked a scale, somehow we understood it. Like Celsius is a great example of that. We went ahead and said 0 will be the freezing point of water, 100 will be the boiling point of water at a certain pressure, and so forth. And so it becomes intuitive to us, but it does not really describe a physical phenomenon. There's no intrinsic physical aspect to the measure. Now, ratio, the number is truly indicative of a quantity that's being measured. And Kelvin scale of temperature is a great example of that. Absolute 0 means something physically. Porosity, it means something physically. 0% porosity, 100% porosity, you just have void, and so forth. Permeability, saturations, and so forth. Now, the categorical was binned into categories, but we could still take a continuous variable and bin it up. We could do that. We do that when we calculate a histogram, and we would call that discrete. We've discretized the continuous variable into bins, and we could suggest that categorical are also just fundamentally discrete. Okay, so those are the general types of features we can work with. Another way to bin it up, and I mentioned this before, quantitative and qualitative. And the way we use it in geostatistics and often spatial data analytics, quantitative means information about quantities that can be written as numbers. You measure it and it comes back directly to you as a number, a metric. Age, porosity, saturation, and so forth. Qualitative, it's really information about quantities that you cannot directly measure. It requires a layer of interpretation. You may have measured porosity and saturation and age, quantitative measures, but now you put an interpretation on a set of samples and say, that's this specific rock type. There wasn't a measurement that you put to the rock face and it said, this is this rock type. No, it required your interpretation. Facies is another good example. Rock types are often used in mining. Facies are often used within oil and gas. And of course, for the geoscientist out there, I acknowledge that there's many different types of facies that we could be working with, right? Depositional facies, different types of architectural element descriptions, and so forth. Lithofacies, of course. So there's many types. Okay, so we have quantitative data types where we have a direct measure, qualitative where we made an interpretation on the data, and now we work with that. That's powerful because something I always say is that much of our data has an irreducible and essential thick layer of engineering, physics, and geoscience, process knowledge, and interpretation. Essential. Okay. We also can break data up into hard data and soft data. I'm going to define this, and I'm going to throw a wrench in the cogs after I'm done defining it. Hard data is data that we perceive as having a high degree of certainty, sufficient to the point where we can deal with it as being precise, certain, no uncertainty. Okay, so often well cores, drill hole core samples, are going to be considered to be hard data. Even often log data is considered to be hard data, that we will not account for the error in it. Soft data are measures that are really usually more indirect, and so they often have a significant degree of uncertainty with regard to the metric that you want to measure. So seismic information shown right here, this might be an inverted seismic attribute. It has a pretty good indicator of where the channels are, but it's providing you more of a probability, a soft measure. Okay, so we call that soft data. Now, I promised you a wrench in the cogs, and this is the wrench in the cogs. I think on my grumpy, cranky days, I could say, I'm kidding around. In my critical moments, I could say in the subsurface, we really don't have any hard data, because every source of data we work with has interpretation. Well logs have all kinds of assumptions required up front about the fluid and rock system, and they can be fooled. They have to be anchored on core. And core data is extracted from in situ conditions, and there's all kinds of opportunities for error to enter in, disruption on the core samples, and so forth. So, hard and soft data. For the purpose of this course, we'll consider things we measure directly as being hard, and things that we measure indirectly and have a high degree of uncertainty as being soft. Now, another way to look at data is primary and secondary data. Not a big deal. This is a relative assignment. It's going to depend on what you're modeling at the moment. If I'm building a porosity model right now, the primary data is all of the porosity data that I've measured at all possible locations, at the sample locations. Now, in that case, I might be using a covariate, and we'll talk more about using secondary information, such as seismic acoustic impedance, which is exhaustively available everywhere at a different scale, and we're using it to support the estimate of porosity away from the well locations. Acoustic impedance in that case is secondary data. Porosity is the primary data, and we're working with a form of multivariate spatial estimation or simulation. Okay, now I mentioned it's relative, and that's because in the next step of the project, you go forward to model permeability. Permeability is now your primary data, but permeability by facies often has a pretty reasonable relationship with porosity. And you already built a porosity model, and so you'll take the porosity, which used to be primary, and now you're going to use it as secondary to support the new primary, which is permeability. So it really does depend on which step you're in the workflow as far as assignment of primary and secondary. Okay, let's do a really quick review. Population versus sample. Once again, the population is going to be that finite set of measures over the entire area or interval of interest, time or space, while the sample is going to be that limited set of data that you've sampled from the population. Okay. The qualitative versus quantitative. Quantitative are features that you can measure directly. You get a number back from the tool. It says this is 13% porosity. Qualitative is a feature that requires more of a layer of interpretation to get to the measure. It would be something like, this looks like it's going to be hummocky cross stratification. My favorite sedge. We've already talked about the issue around bias sampling. We even told the story about 3 different levels of bias, that horror story that I shared, horror stories with Professor Pyrcz, and that's in the previous lecture. So we know that there's going to be issues with bias. And we already defined prediction and inference. Everything we're doing is going to fall into those 2 buckets. Prediction was given a model of the population, model of the system, predict the next sample or next outcome. Inference, kind of more difficult, is given a limited sample, and I've said this before, I'll say it again, we sampled but 1/1,000,000th of the subsurface directly. Geez. Take that sample and now describe the population. That's a tough task. Now let's talk about different types of data. It's going to be a very cursory treatment, to be honest, and I'm going to say something here. I'm not a petrophysicist. I'm not a geophysicist. I'm an engineer. I'm a geoscientist, but I'm not an expert in all these data types. So it's going to be just a limited discussion just for awareness. It would take multiple classes anyway to really cover this. There's great classes on petrophysics taught by Dr. Torres Verdeen in our department. I recommend that if you want to jump in and learn more about it. And there's great books on the subject too. We're just going to explain, summarize, but we're going to focus on what I think has the most impact on geostats, data analytics, and machine learning, and that is coverage, scale, and information type. That's what intrigues me the most. Coverage. What proportion of the reservoir or the population or the subsurface do we have this data available for? How much of it is covered? Is it just a couple of meters around the well at every well? Is it just limited locations within the well bore? Is it everywhere, the entire subsurface? Scale and support size. What is the scale of the individual measures? What is the level of detail I can see? Is it pore scale? That would be great. Or is it in fact at many, many meters, vertically, tens of meters, aerially, hundreds of meters? Or maybe it's just a measure that kind of gives a sense over an entire reservoir unit within some drainage radius of a well. And the information type. Given coverage and scale, what's it telling me about the reservoir? They don't all tell us the same thing. Is it telling me about the grain size, the fluid type, the layering, the framework, the porosity of the system, the pore volumes? So let's go ahead and let's remember, this is going to be cursory. Don't be too judgy about this. So, core data. If you have not had an opportunity to spend time in a core lab, I highly recommend it. The Bureau of Economic Geology has an excellent core lab. You could contact individuals like Dr. Jake Koval with his group and check out and see some of that core. I know there's others who work out of there too and have great core examples to look at. Time well spent. So first of all, core data is expensive, time consuming. It's very infrequently collected in most examples. Incomplete coverage of the well. Now, if you're mining, it's much more common to have core samples extracted with their diamond drilling. They do a lot more coring through the actual resource rock that they're working with. Okay, but for oil and gas, it's usually pretty infrequent. Very in select locations. We work at great depth. We've got to trip all the way out, put the core barrel on, go back in. It slows down ops, but core is essential. It is literally the anchor for many of the things we understand about the subsurface. You can actually look at and touch the rock. You can get quantitative measures such as grain size, porosity. There's tons of opportunities to do interpretations to support the entire framework, the entire interpretation of the subsurface. You'll look through and you'll see different types of structures, ripple structures that tell you about transport and deposition. Maybe it's more massive structures that tell you that you had a massive load of sediments dumped at once without any transport after the fact, resulting in a lack of sedimentary structures, just massive nondescript. You might have specific layers of mud and sand that tell you that you'll have issues with permeability anisotropy in the subsurface, and you might even be able to look through and see ichnofacies. For example, you might see something like thalassinoides or Orpheomorpha, which will tell you about the paleo. And that is just amazing because now you can put things together. Was it shallow water, deep water, high energy, low energy, nutrients? What was going on in that setting? I have a lot of respect for what gets done with core. I've had the amazing experience of spending time with individuals like Tim McCarg, Nick Drinkwater, Morgan Sullivan, Henry Postmentier, and others in core laboratories and being able to look at rock with them. I even had the chance, and it was a wonderful opportunity, to take in the short course with George Pemberton, who unfortunately recently passed away, but one of the world's leading experts in ichnofacies. I taught an amazing short course, also was a professor at the University of Alberta, where I came from. So just amazing individuals. Now, more on core data. There is routine core analysis, and you can take the core and you'll have an entire whole core. And usually what happens is you can break it up And then what you could do is you could divide it further by taking core plugs, and you can decide to take those samples and test them for porosity, permeability, saturations, and so forth. You might also want to run calibration on them based on what you would image with gamma, like a gamma ray type of measure. And so you can calibrate, and when you do the well log later, and I'll talk about well log, you're able to then figure out exactly what it means. You've benchmarked, you've datumed it with the actual rock. Core tomography is amazing. You do a scan and see the pore structures. There's a great online resource. Dr. Prodanovich has a digital rock portal, which you can visit and access all kinds of great core tomography type of data sets where you can actually do analysis on pore structures. I think that's just radical. That's awesome. So check that out. Spatial core analysis, you can go much further into it, calibrating with spontaneous potential, SP, nuclear magnetic resonance, mercury injection. You can get the distributions of exactly the pore throats. That a lot if you're trying to figure out the behavior with respect to imbibition, wetting, getting into multi-phase behavior as you're trying to figure out exactly how fluids are going to flow through the subsurface. Okay, so this is very powerful. Let's go ahead now and talk about well logs. Now, once again, I'm not a petrophysicist, and there's a lot of great resources if you want to learn more about petrophysics and well logging. Just to mention a couple of common well logs. Now, first of all, they're all going to be indirect measures of the subsurface. We're not actually extracting rock and doing a direct measure on the rock. We're doing something to indirectly make a measure of the rock. Now, resistivity and spontaneous potential, they're really good at showing bed boundaries, fraction of shale, fluid transitions and changes. Gamma ray is great because it'll tell you if you have organic rich shales that are present, and they'll show up. You'll see that increased activity. Nuclear magnetic resonance, well, originally adapted from medical imaging, responds to the presence of hydrogen protons, and it's going to tell us about the types of fluids that are present in the subsurface. In the last while, there's been an increased use of image logs. And this is a really, really cool technology because what we're able to do is if you look at this tool right here, you can pull that up through the well and you have all of these button electrodes that are oriented around the whole 360 degree of the well bore. And as you come up, you produce these tracks at high resolution. Like 80% of borehole coverage at a resolution of about 1/5 of an inch. You have sometimes a depth of penetration into the rock of maybe up to about 30 inches. And you actually, it's like as if you're imaging the whole wall of the borehole. And it's fascinating because, so let's take a look at a track right here. This is a turbidite levee deposit, and they're known to be commonly interbedded. They're going to have coarser grain and fine grain deposition, and they're often dipping. Well, look at this. It's really cool. You can see the transitions and facies going from maybe coarser to finer, coarser to finer, coarser to finer, and you see this pattern right here. That's due to the fact that you have a borehole intersecting and dipping beds, and you see that perfectly. Here's a case where we have a slumped sandstone. So this would be like a mass transport where all of the rock failed together. And the result is it got kind of churned up. Some of the mud in it was perhaps more ductile and was able to bend and be deformed as it was transported. And here's a breccia where you can actually see the class and the matrix associated with this type of failed and transported type of rock. All right, so these are amazing. You can see all kinds of amazing structures and understand the rock. It's like you're going down the wellbore and looking at the rock at a high resolution. Very interesting measures. Seismic information. Well, there's so much we could say about geophysics and the use of reflection surveys, seismic reflection surveys. Just in general, I'll just generalize here and say that what we typically will do is we will design and shoot a seismic survey. We will then go ahead and invert from the original amplitude information and get properties that are more related to the rock. Acoustic impedance might be correlated pretty well with porosity of the rock or other types of facies changes. So we're going to want to ground truth it with a seismic logs so that we're able to put things in the right place relative to the well data, and also calibrate and understand how specific rock and fluids respond in the seismic. It's an indirect measure, of course, and everything else must be calibrated directly to core information too. In addition to absolute rock properties and space between the wells, it does provide us with an overall understanding of the framework. We can see the layering, we can see the transitions or changes that occur, and we can try to investigate that. Often in exploration, our ability to find structures, stratigraphic and structural features that could pose opportunities for reservoirs with traps and seals and so forth will come directly from analysis of framework within seismic. Now, I've heard once before that the only real hard data we have is production. That's the one thing. It comes out of the ground. We know exactly what comes out. If it's a water aquifer, we know what comes out of the ground. We can measure it directly. We can analyze it. And if we're in oil and gas, it'll of course be hydrocarbons too. Production data, there's a variety of different measures we can work with. Bottom hole pressures, the fluid production rates, and so forth. One challenge we have is often production is going to be commingled over long completed segments of the well, and we may not know exactly where it's coming from. We may have the ability to use production logging tools, PLTs, like the one shown here, where you pull the tool up and it can tell you the flow rate. And then we're able to look at a cumulative production curve right here. And this is fascinating because we can look at it and see, okay, we have some production coming from this area, no production, then some production from this right here, some production from this. Now, this is fascinating because in this case, it looks very discrete. Maybe this is related to some type of fracture framework where we're getting most of our production from very short intervals over the well. Okay, so this is really interesting stuff. We can use this to figure out large-scale permeability, connectivity, the overall volumes up to a distance that we're sampling, which would be known as the drainage radius over which we're producing. Okay, so if I wanted to talk about the various different types of data, I mentioned, well, we have different types of data, and then we're concerned with the resolution, the coverage, and the information type we gain. We could summarize it like this, and this isn't perfect. This is just a kind of rough assessment. I'm sure there's things I've missed here, but it gives a general sense. Core data, the resolution is unlimited. You only have coverage rarely in the wellbore, not at all locations, but at select locations, and it tells you lithology, pore, sedimentary structures, the depositional setting. Well log information, well, the resolution is going to be decreased, but you have some depth of penetration into the rock away from the wellbore, and they're very good at trying to figure out overall facies at a larger scale, the porosity, the mineralogy. And when I'm talking facies, I'm talking about depositional facies, the lithofacies, and so forth. Image logs, well, they have increased resolution in that 360-degree imaging of the wellbore. Very cool. And they can be quite common too in some settings, telling you information with some, maybe a less depth of penetration than some of our well logs. And they'll tell us directly about sedimentary structures, dips even, and you might even be able to observe like really cool things like humming cross stratification, one of my favorite sedimentary structures, again, faults and so forth. Perhaps. Seismic information resolution is greatly decreased. Vertical resolution may be 10 meters. Tens of meters, and aerial extent often hundreds of meters in the horizontal direction. Coverage is now exhaustive, so what you lose in resolution you gain in coverage, and you can see the framework, the trends, facies structure, maybe facies and porosity if you are ground truthing with available logs and core information. Production information, well, a much lower resolution. Again, really, the coverage is only drainage radius around producing wells, but it's telling you about overall volumes, pore volumes with fluids and connectivity, and a very gross measure of permeability. Now, there's a lot of data types that I did not talk about that are really important. Mature fields, they're wonderful. If you have an analogous mature field that has been producing for a long time with a lot of data, that can be very useful for making assessments at your new location. You got to deem that's analogous. The statistics are consistent. Outcrops can be very powerful. Once again, it's like having core. You have infinite resolution, usually only in 2D, but with reentrance and multiple outcrops, you can piece together more of a 2D plus the 3D type of image. Coverage is really none. You're working with an analogy. You're working with rock that you deem to be similar to the reservoir. It's quite rare to have an outcrop that's actually the same formation, and even in that case, it's going to be different because of the fact it's been exposed to the surface for some time and unloaded. Concepts, input statistics, and so forth. Geomorphometric type of studies are really fascinating. Often the geomorphologists are focused on surface earth processes, and so they have infinite scale, and they can understand how rivers and deltas and carbonaceous settings like reefs, how they evolve over time. You don't have coverage here because it's analogous, but you can learn a lot about the concepts, the geometries, and what might be going on with your reservoir. Shallow seismic is beautiful. I've attended quite a few talks and had the chance to work with Henry Post-Cimetière in the past. Amazing. Those types of studies where they look at the high resolution seismic that is sitting on top of the reservoir, and if it's deemed to be analogous, the same type of processes, you can image and step through time and see how things evolved. Just amazing stuff. Concepts and input statistics. Experimental stratigraphy. I'm a big fan of Jurassic Tank. Our friend Professor Chris Paola and all of the amazing things going on up there and all the great grad students, where they're taking these massive tanks and they're pouring in analogous materials. Maybe it's fine grain type of particles and with different types of attributes. They try to scale it and they put water in and they look at how things behave over time. They run very focused experiments on how the interactions of tectonics, sediment supply, and eustasy account for different types of predictive patterns that we can understand in the subsurface. And numerical process models. We're getting to the point where very complicated computer programs are able to simulate the actual deposition and formation, preservation of the subsurface, and we can learn a lot from that. I've seen great work. Tao Sun out of Chevron in the research center done really amazing things that have been published, and I welcome people to look at that. That's great. And of course, there's others around the world who are working in this field. Resolution? Well, in that case, I should say, with the numerical models, you really do have infinite resolution. I should change that because you're able to observe exactly what's going on grain by grain or a very small finite volume by finite volume. And so, of course, analogous, and you can learn a lot about concepts and predictive type of geometries and predictive models. All right, so I hope this discussion about data types was useful to you. In the next lectures, I will get much more into probability, Bayesian probability, frequentist approach to probability, and how we use probability to support our statistical analysis and decision-making modeling for inference and prediction. So, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. And I put out resources on GitHub and on Twitter. You can find me, I'm the Geostats Guy on both of those platforms, and my YouTube channel is Geostats Guy Lectures. All right, I hope this was helpful to you. All right, take care.